Recently, my favorite YouTuber and idol, Grant, launched a new video. It's a counting problem which can be solved by complex analysis perfectly. But Grant also encouraged me to try another ways to get our goal. So I tried and find another magic in group theory, which helped me get over the mountain. It's Burnside's lemma. We are dealing with counting problem, so I tried just counting and reveal some more fundamental idea about symmetrics. Then I solved this problem nice and perfectly. Today, I'm going to look through 3 puzzles which are all about counting problems which involve the group theory. I'm going to introduce you a counting lemma in group theory and combinational math. The Burnside's lemma. Don't be afraid of the formula. I'll explain it to you, and trust me, you will give more deep thoughts than just a famous formula. So let's start. The 3 puzzles are as follows. The first about music, the total number of all distinct triads. The second about chemistry, the isomeride counting on benzene ring. The third, we back to math to look back to the recent 3B 1B puzzle, the Olympiad level counting, which bring us some more deep understanding about the symmetrics. So first, let me explain this puzzle. First, we need to know what is the 12-tone equal temperament. It's a musical concept which divides the ratio between any octave into 12 equally ratio. I may represent these things by a sine graph, which looks like a clock. And when I mean triad, it was just choose 3 numbers on this graph, or 3 vertices on this graph, which must be different from each other. We want to count the triads, so let's just write down a triad in 3 ways: the piano, the sine graph, and some numbers. As we write down those triads into a formalized numerical way, we can ask a question: how many sets which contain 3 different integers from 0 to 11? Well, that's very easy. It's just the same question as choose 3 things from 12 different things. It works out to be 220. It seems a lot more than we expected. Let's just put all choices in a set. We may call it X. Let's back to play and write a bit more. We can find by some rotation actions. I may represent it by an image. It forms a related but different triad. So we might guess each distinct triad has 12 different copies in X. So we happily divided X by 12, and we got So we date back to our thoughts. We supposed that all elements in X, such as 0 to 4, have 12 different copies in X. Here I draw some graphs to illustrate how the actions actually generate all the 12 different elements in X, but actually they are the same tracks. I organize them by rotation actions, and you can see how the 12 copies in X actually the same tracks. But as we go deeper, we found some element in X don't have the full 12 copies. They have just broken and have less than the 12. For example, the 0, 4, 8 elements only have 4 copies in the X. I also draw a graph that organized by actions, and you can see how the 12 things are divided into 3 same things, which each of them has 4. So, what Burnside's lemma say is that we shall first complete the loss and errors caused by symmetries, and then divide off those copies by the size of the group, which tell us the total copies of the symmetries. The Burnside's lemma actually found the orbits, which denoted by the X divided by G and its size symbol, and the notation X power to the G is not represent for the power, it's just a notation. It means the element in X which do not move or keep stabilized by the action G, and they consist a subset, and we denote it by the X power to G. We sum up the subsets of the action G, and we get the complete version of the set X, which fix those errors and losses, which we can safely divide it by G. In this page, I try to do as much I can do to draw some illustrations that what does this stabilizer, but actually you ought to just try by yourself or just ponder for a moment that the stabilizers summed up is actually fixed the errors, and try to understand what I wrote on this page and just play by yourself. Just be playful. I highly recommend you to just cut a circular shape by using your paper, and you just draw some dots on it to represent the tune that you play. And you can just rotate it, and you can just see that it doesn't actually move, and you can check how many different things are there and just be playful, and you can find the symmetries behind it. No flippings around because it's just some rotations. So just made it by yourself and just do it and be playful. To count all isomerides of a certain benzene compound, we must know what is benzene and the isomeride. The benzene ring is just a hexagon modeled compound we may draw or model like this. And the isomeride means a family of compound has the same composition but different constructures. In our certain problem for a certain compound, I just mean it has a ring or a hexagon and the same substituent group A, B, and C. For example, these two compounds on screen are isomeride to each other. So now we have found two of them. We want to find all of it. In the previous puzzle, we can easily see that the all copies generated by the symmetries all add up to 12. So this time, we want to know all the symmetry of a hexagon. Here is the hexagon. I highly recommend you to make things like this and play with me to find all the symmetries of a hexagon. Here we allow flips like this. So first I have some notifications of the vertices so you can track the symmetries. So first let me set these things to be the fixed with which there's no actions act on it, and we can just see some act. You can find some symmetric actions like this, and you find some vertices has replaced, and also you can to get it back, which means there always has a reverse of your actions. And you can see if we don't flip the hexagon, there will have 6 of the symmetries, and we get back. And if we flip it, and we have another 6 of it. Let me show you how this works. Focus on this. It combined 2 actions which flipped and rotate, but this can be just by flipped by these actions, and you get back, and if you do it again it brings you here. So the actions could combine with each other. So go to explore and try to find how many symmetries, of the total symmetries of a hexagon. Let's summarize this. First, we can rotate it to generate total of 6 symmetries. To draw these things, it seems boring, but trust me, it's worth to our understanding. Then we found it could flip, and to the flipped hexagon it has another 6 symmetries, which add up to 12. Now, as we know G, we can just figure out the whole number of x. It's just to put the 4 substituent group to 6 different positions, and it works out to be 180. And for each actions, we want to find all elements in X that fixed under this action. Try to draw which I did not draw. Trust me, you can figure out by just drawing. To find out why under some actions there are no such things that we expected, but under some others it was. So here I made a hexagon by some papers and 4 substitutive groups which has different colors, represent A, B, C, and C. And let's just see how this hexagon symmetric acts on it. So first, I label some notifications on the vertices to track the symmetries. You can see you can rotate it and it stay fixed in the space, and you can flip it, or you can flip it and rotate it. It doesn't matter. And I will show you how it generates the 12 different things and how it remains stable in some kind. So let's just show one kind of things, which is the arrows that we want to fix. I highly recommend you to just handmade things like that, like this, to get better understand of the things, because they are just not that much difficult. It's just you need to play yourself and you can know it better. Yeah, I had done this work, and you can see if I flip it and it remained the same, and that means you will lose the things, so that you want to pull it back and fix it so that you can divide by 12, which is the size of the group. So just make things like this and play by yourself. You could understand much better. In this reflections part, we mainly focus on the orbits. here we have two puzzles, and you have already know how these two puzzles related on the countings and the symmetries. In this reflection part, we just focus on the vertices of each symmetric object and to draw the actions and how the actions effect on the vertices by some arrows. Go and try if you can figure out what these orbits mean and how it's represented by the vertices and the arrows. Focus on the orbit and try to figure out if you can understand the copies I mean and what the loss means exactly. So finally, we back to the math puzzle. The original version of this puzzle is as follows. You have a set containing integers from 1 to 2000. We can easily know there are 2 to the power of 2000 subsets in total. If you don't understand, go to look the videos that Grand made. And here we want to count our subsets whose all elements sum can be divided by 5. It's hard, so we make a simpler version. Take a smaller set which contain integers from 1 to 5. It's easy to know it has 2 to the power of 5, which means 32 subsets. So let's just play around to write all the 32 subsets. There are 5 sets contains 1 element, 10 sets contains 2 elements, and 5 sets contains 4 elements, and another set contains 3 elements, and each one of those sets which contains none of the element and all of the elements. I arrange these subsets in the column of the residue class, so we can easily see these subsets evenly distributed in 0 to 4, which means we just want to divide those things by 5. Similarly, we have to fix some errors. To associate these things with Burnsett's lemma, we want to find some kind of symmetric actions. We can just try to put all subsets in a new set and call it x. Of course, the size of x is 2 to the power of 5. Works out to be 32. We want to have a rule to associate several elements in x. If you have read a lot in math, you may guess. Because we divide things, we naturally come up with the cycling group of 5, which name is C5, just like the first puzzle, which have a C12 group in it. This cycling group has nice relations with modular addition in integers, so it's worth to give it a try. Similar to the first puzzle, cycling groups has some rotations as actions, so we construct those numbers to wind a ring and we rotate it. It seems good. It means we find a reasonable actions to relate those things. But I also encourage you to construct another constructions to fit all these properties by yourself. We back here to play again, just to try to associate 5 copies by the actions I showed in the deep thoughts. It seems work well. you can always find 5 copies for certain elements in X, and it can generate exactly 5 copies by the actions we defined. We also find errors. Now we can do some calculate. By this way, we successfully associate 5 copies together in X. I have illustrated it on the paper and try yourself. If you can understand these abstract things, you can just try to relate those things to the previous 2 puzzles, and that will be helpful. Now let's focus on the lost term. The empty set, which its cycle is just 1, so it lost 4. And it do the same to the full set. Under each actions, there always these 2 guys make some error. So we count each size of these stabilizers is just 2. Now we just to use the Burnside's lemma and to work out 8, and it exactly worked. You come back to the playground to find some reasons of this result. Now let's back to the original version. We want to solve the original version, and we want to present the symmetry structures. So if we use cycling group of 2000, it would not be the case, because it represents a modular which divided by 2000. Now is the most excited and burst out moment. I highly recommend you to pause and ponder, try yourself to construct a structure that fit our requests. Well, I'll show one that I found. I multiplied the cycling group of 5 400 of times with the Cartesian product to construct a group to fit our original version's puzzle. Now, instead of 1 ring, we wind several rings. In each ring, it contains exactly 1 element of each residue class once. You can just think like that there's a lot of rings which contains 1 to 5, but they are actually different elements. This evenly distributed properties does help a lot. The 2000 could divide it by 5 after all, and that makes things more easier to construct these structures. For most of the subsets, for example, like I illustrate on the paper, they do cover all 5 copies in the X set. In this example, you have 2 parts, and in this case, it seems like has 2 freedom to span a 2D plane. However, we can just rearrange these things in column or in row, whichever doesn't matter, and it do have 5 copies. For higher dimensions, it behave the same. So the errors would only happens when the subset has span nothing, it's just a point. In this case, we have to fix those 4 losses back. And to count all the annoying subsets here is also quite easy. It's just 2 to the power of 400. And finally, we got the same answer as the complex analysis does. In the final, there still some things remains, but I think you can figure out yourself. The first is about the evenly distributed properties. you can go back to the play around sections and just to figure out how these things contains to our original version of the puzzle. Here I just write the answer and you can try to figure it by yourself. You may have wonders same like me. What about the answer which the size of the original group does not divide 5? For example, what does it behave if the original group size is 6 or just 2001? Well, that could be easily solved by just to extract those things which do not have 5 parties to play with it, and we just to count these things separately and combine with the distribution evenly properties, we can still easily solve these things. And here I have some draft of these things and you can have a look of it, and still I recommend you to do it by yourself. I don't want to be the spoiler. So have fun and good luck. Oh, it finally finished, and during this journey, I think you have found some more deep thoughts of this world about symmetric and things like others. Of course, this is not about some deep math, actually, because I'm just an amateur to math. I want to learn math and to play and to feel the truth of the world. It's just beautiful, and when I just understand the world, I feel really, really good. It was just excellent. When I learned these stuffs, I could actually hard to find things like this. So I decided to make something. So you have seen this video. When I learned these things, I just saw the obscure formula and the lemmas, but I want to know it, and I believe that this world, the truth of the world, ought to be beautiful and elegant. So I just play and find and thought, and finally I get some understanding, and I just share it with you all, and I hope I can do something to help you, and I will be very, very happy that if I can just help you to love math or to understand the truth of the world, and it takes the worth, and it totally paid off. At last, thanks for your watching. Thank you very much to look until the last of the video. Just have your days and wish you love math ever, and bye.